Hello. So today we're finishing up chapter 28, and this will be an extension of some of the work that we talked about, especially around the photoelectric effect, where we saw that light has this particle nature to it that we called photons. But now we're going to take a look at a even more bizarre phenomenon that's connected to something that you've seen before, which is two-slit interference, and we'll talk about that in just a minute. Before we get started, I'll go ahead and give the announcements for today. We are finishing up chapter 28. For next week, please start reading in chapter 29, where we're going to look at some applications to some of the quantum stuff that we're discussing this week. We'll be expressing how this relates to things like atoms and molecules, and especially looking at some of their energy levels and some of the basic outcomes for that. Our homework for chapter 26 is due on Thursday, April 23rd, and our homework for the chapter 28 will be due on Thursday, April 30th. Please come bring your questions during our normal meeting hours, and we will from 5 to 6 p.m. on Mondays and Wednesdays. There will be Zoom links sent out for those meetings, and I look forward to talking with you more about those things. Okay, so I'm going to also go back and forth with some simulations today, and I will post the links to those simulations on the announcements and as well as in the comments or how do you say, the description of this video. So you have seen the double slit experiment before. Waves make this interference pattern where you see sort of a bright interference fringe at the center, and then you see some dark spots, and then bright, and then dark, and then bright. And then basically seeing an interference is strong evidence that there's a wave nature phenomenon that is taking place. But it might sound like a little bit of a bizarre experiment to try, but what if instead of using a light source, we were to use a single photon source, or even weirder, a single electron source? So I'm going to demonstrate what I mean by this by opening up simulation here. And you can actually, you know what I'm going to start with actually first is I'm going to look at there's this, there's two sort of simulations. One of them is kind of the more modernized so-called wave interference, which is the classical wave interference that you've seen before. And then I'm going to relate it to the so-called quantum wave interference. So let's see here, it should be loading. Just load it again. Okay, so the classical wave interference, just to sort of remind you how this works here, is that we can actually see interference between two waves, whether it's water waves, or whether it's sound waves, or whether it's light waves. We see these interferences between them. So for example, here are sound waves, and you have high pressure and low pressure places, and they interfere with each other, and they make this kind of crazy interference pattern. Maybe you remember doing an experiment with me earlier this semester where everybody lined up, and you actually, as you lined up, you found places where it was louder or it was softer if you're in the middle of this place here, or it was louder or if it was softer, depending on where you were standing. The same phenomenon also happens for light. And so here we have two light sources, and these look like laser pointers, but they're actually spreading out their light. And then they make this light pattern, which is going to be bright here, dark here, bright here, dark here, etc. So this is the interference of light. Now that's two sources interfering with each other, but the same phenomenon actually happens when we send a wave into a single slit. It spreads out. And so if we change the slit to two slits instead, it's as if we had two sources here, even though it's coming from the same original source, and we get a diffraction pattern. So the diffraction pattern is telling us that there are, let me make it two slits again. The diffraction pattern is telling us that there really is a wave interference happening, right? So that we get this bright spot in the center, dark, bright, and then dark, and maybe we get another bright one over here. So in other words, the sort of headline here is that seeing that so-called diffraction pattern of bright, dark, and so on, is telling you that there's a wave nature going on. So far, so good? Now we're moving on to the quantum interference. So in this case, I have a photon. Basically, it's a high intensity beam, and what I can actually do here is, well, here I'll do it like this. Well, we have we have some photons coming out from this beam here, and when we do this, we actually see this intensity pattern building up here. So it's bright in the center, dark, bright. So this is telling us that this is not just a particle phenomenon. In fact, what would we expect if they were just particles? Well, I would expect that we would just get a bright spot here right behind this slit and a bright spot right here behind this slit. And maybe there'd be a little bit of spread, but that's what I would expect if they were just particles. But the fact that they are making this bright band in the center, dark and then bright, this implies that there's an interference effect happening, just like we saw for waves. Now let's do something a little differently. Let's take that same photon gun, and we're going to do the same experiment, except I'm going to just send one photon through. So I'm going to hit the fire button. Just a moment to see how does this work. Oh, okay. I'm going to hit the fire button here, and we just see one photon developed on the screen. In fact, this is actually how old cameras worked. Like maybe some of you have 35mm film cameras where the light that hits the film actually exposes the film, right? And then there's little dots that will show up basically where photons hit. So if we repeat the experiment again, another dot appears. Okay, but it appeared in a different place. We repeat the experiment again, and a different dot appears. Let's speed it up a little bit. So we're going to have the experiment repeat a few times, and I am also going to speed the whole process up here. Sorry, my computer's a bit on the slow side. You see it's working really hard to think about everything that I'm asking it to do, but what's happening is it's simulating. Okay, sorry, it's just a slow computer. But this is happening many times here. And as we are watching these photons hit the screen here and so-called like develop the screen, one of the things that's interesting is that we're actually beginning to see the developing of an interference pattern. But this should seem really strange to you, because why should that happen if it was just one particle? It implies like that the single photon, like as if it went through both slits at the same time. But that's kind of weird, right? Because why would a photon go through two slits? It's like if it's really a photon. So in other words, this experiment is forcing us to expand our definition, to think about it a little bit differently, our definition of what photons really are and how they work. In other words, that there is a particle-like nature to them, this fact that they develop at the screen, but there's also a wave-like nature to them, which means that the way in which they are developing follows the rules of wave mechanics. In other words, there's an interference that's happening. So very strange stuff. But hopefully you've seen now enough of these photons hitting the screen to see that there really is a pattern emerging. And in just a moment, I'll show you a slide that gives you sort of another sort of perspective on what this pattern would end up looking like. Okay, so here's that sort of experiment here, and we're looking at photons coming in, or even electrons, making a dot on a screen. And if we repeat the pattern many times, repeat the experiment many times, they're going to build up this interference pattern. So what are they interfering with? Well, apparently themselves. So it's a very strange thing, and it forces us to give up our common sense of the notation of the notion of a location. The experiment, for example, maybe first looks kind of random, some more random dots, but if we do the experiment long enough, we see really these interference patterns emerge. And you can look at this website here to see how Hitachi actually demonstrated this experiment using an electron gun. Okay, so the point here is that both electrons and photons, they have this particle-like nature and a wave-like nature. So here's our challenge question. We're trying to figure out something called a de Broglie wavelength of a baseball. And we have a speed of 30 meters per second, which is about 60 miles an hour. It's a pretty fast baseball, but doable. And we'd like to know what is the de Broglie wavelength, why you can't see its so-called waviness, and what the speed and the momentum of this baseball is if it had a different de Broglie wavelength. So let's go ahead and take a look at some review here. So the de Broglie wavelength is equal to this Planck's constant divided by mass times velocity, in other words, the momentum. So in other words, the higher the momentum, the shorter the wavelength is. So let's apply it to this situation here. Going to my camera, if the de Broglie wavelength is equal to h divided by mv, then this is equal to 6.626 times 10 to the minus 34, and that's joules times seconds, divided by, we said it was 150 gram baseball, so that's 0.15 kilograms. And I think that we said it was 30 meters per second, if I'm not mistaken. 30 meters per second. Okay, very good. 30 meters per second. So, in other words, we've got here, it turns out that these units are all going to work out to be in meters when we use SI units, which is probably not surprising. I can work it out here. It's just a joule, if you remember, is a Newton times a meter, which is a kilograms meters per second squared. Oops. So then meters times meters is meters squared. And then we have down here on the bottom kilograms. We have a meters per second down here, so meters and seconds. And then finally we have a joules times seconds, so it's going to be seconds squared. So seconds squared cancels out, meters cancels out once, kilograms cancels out once, we're left with meters. And that was a little fast, but I encourage you to work out the units on your own, thinking that joules is a Newton times meter, and you can come up with the units of meters. Good thing to do just once, just to make sure that you understand how the units are working. Let's get out a calculator. Calculator says I need to put in Planck's constant, 6.626 times 10 to the minus 34, divided by 0.15 times 30. Wait a second, that's pretty weird. So the de Broglie wavelength is 1.5 times 10 to the minus 34 meters. Well, I have to say that's a very, 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 very small number. 10 to the minus 34 meters. So, maybe that helps explain for us why we can't see its waviness is because the size of a baseball is much, much larger than 10 to the minus 34 meters, right? It's on the order of about 5 centimeters or so, right? So 5 centimeters compared with 10 to the minus 34 meters, it's no wonder we can't see the waviness of a de Broglie baseball. Okay, so what if the de Broglie wavelength of this baseball, I'm sorry, it said it had 200 grams, not 150, but I think you get the point. It doesn't really matter, honestly, like in this example. What is the speed momentum of a 200 gram baseball with a de Broglie wavelength of 0.2 nanometers? Well, let's flip the equation over and let's say, well, we're going to look for, we're going to look for, we want to know what the speed or the momentum is, right? So in this case, let's do P is equal to h divided by lambda. So in that case, again, we're going to use this 6.626 times 10 to the minus 34 joules times seconds, and we're going to divide by 0.2 nanometers. That's times 10 to the minus 9 meters. Now, if you trust the SI units, then we can just do this number 6.626 divided by 0.2 times 10 to the minus 9. So we get 3.3 times 10 to the minus 24. And the units of momentum is kilograms meters per second. And if we wanted to figure out so that's P, and that's going to be equal to mass times velocity, right? So if we wanted to figure out the velocity, well, we could just divide by the mass, right? So we could divide this by the mass, which is actually 0.2 kilograms. So the velocity is actually equal to 1.6 times 10 to the minus 23 meters per second. Huh. Well, that's rather slow, right? So in other words, what we're looking at here is that we're seeing some surprising results here in terms of that for macroscopic objects, we're not really talking about the same speed and length scales as the de Broglie wavelengths of this of the quantum world, right? So let's go a little bit deeper and think about if matter really does have kind of a wave-like property, like we saw from this double-slit experiment, then should we be able to get these so-called like standing matter waves if we put this particle into a box? So what if we wanted to make the minimum energy of the electron to be some nanojoules, right, or 1.5 times 10 to the 8 joules, 10 to the minus 8 joules. Let's take a look at this situation here. So if we put a particle in a box, that means that we're actually confining it. Then there can be matter waves that, as the particle is bouncing back and forth, it's interfering with itself, and it makes these little lobes, just like we saw with waves on a string. And so it turns out, and I won't derive this equation, but I'd be happy to entertain you with that if that's something you're curious about, that we can get these different energy levels that scale as the number squared, and that number is going to be the number of these lobes here, and then divided by the length of the box squared, and then we have 1 over its mass. So in other words, there's these discrete energy levels that actually take place. So, and the lowest level is going to be the n equals to 1 level. So let's give it a try here and see if we can compute the lowest energy level and figure out what length of a box we'd actually need for confining an electron. So I'm going to write down that the energy lowest that we want to get is 1.5 times 10 to the minus 8 joules. And we're trying to figure out what is the length of the box that we need. So I'm going to now go to my board here, I guess you could say. And the energy is equal to h squared n squared over 8ml squared. Let's double check that formula, make sure it's correct. H squared n squared over 8ml squared. Good. So in other words, if we wanted to figure out what L is, we have to do L squared is equal to h squared n squared over 8m and then E. And if we take the square root of both sides, then we'll get L. Okay, very good. Well, we decided that the lowest energy is going to be for n equals to 1. Oops, n equals to 1 for the lowest energy level. And now it's a matter of plugging in some numbers here. Well, we know what h is, right? That's 6.626 times 10 to the minus 34. I'm not going to write the units this time. Times 1 squared divided by 8. M is 9.11 times 10 to the minus 31 kilograms. And the energy that we're desiring here is 1.5 times 10 to the minus 8 joules. Okay, very good. So I'm going to plug in all of this into my trusty calculator, and we'll again use Planck's constant. So we'll do the square root of Planck's constant times 1, okay, it was 1 squared, divided by 8 times the mass of the electron times 1.5 times 10 to the minus 8. All right, so that's our number. And we get that this is a box of 77.9 meters. So in other words, even if you have a box that is this large, then you're going to get energy separations that are on the order of a nanojoule. Okay, so let's a nanojoule turns out to actually be quite a bit of energy, or well, this is some fraction of a nanojoule here. And so if we go to even smaller length scales, well, we saw that the energy goes like 1 over L squared. So that must mean that the smaller we confine something, then the larger the separation is going to be, the larger the energies are going to be for the different energy level spacings. So here's the energy level for an electron in a box in a quantum system. So it's kind of an approximation for an atom. So why is it an approximation for an atom? Well, it's because the way I like to think about it is that we sort of have this picture. This is sort of a rough picture of an atom, is that you have some positive nucleus, and then you have the electron sort of going around it, right? And, well, it's sort of confined to this distance here, right? It can't go outside necessarily. It's sort of confined in this area. So it's not such a horrible approximation to imagine that there's this electron that's kind of able to go backwards and forwards, but it really can't leave the atom, right? So that's the kind of ideal. That's why we're saying particle in a box. That's the box is kind of that it's being bound to the atom somehow. So let's take a look at what wavelengths of light could be emitted for this atom. Well, here, let's see. I'll first do this here. We can have, now I'm going to actually draw this on the slide itself here. I think that makes some sense. So we can have transitions that go from the E3 to E2. The difference in energy between these here, for example, let's just say this here, that the difference is equal to, what is that? 4 minus 1.5 is 2.5. Oops. 2.5 eV, right? So in other words, that difference in energy so we have a delta E is equal to 4 minus 1.5 eV is 2.5 eV. And I'm going to actually show you a cool trick here, is that if you wanted to convert from eV to nanometers, there's a nice little trick that you can do. You don't have to do this every single time. This energy here is going to be the energy of a photon that's released. And if you wanted to convert that into a wavelength, you can always use hc over lambda. That's okay. But this number here, this hc, turns out to be equal to 1240 nanometers times eV. So in other words, if you ever have an energy, you can always write 1240 nanometers times eV, and then you can just divide by the wavelength in nanometers, and you'll get eV. Similarly, you can also divide by the energy in eV, and you'll get nanometers. So let's flip this equation. We'll say that the wavelength that's in nanometers is going to equal to 1240 nanometers eV divided by that energy, 2.5 eV. Now when I do that, I'm going to say that 1240 divided by 2.5 is equal to 496 nanometers. That was a lot easier, right, compared with our previous thing where we actually plugged in H and we plugged in C. You can certainly do that, but this is a faster way of getting there. And so this is our wavelength that's emitted. So in other words, going back to our slides, the difference in here is 2.5 eV, or in other words, 496 nanometers between n equals to 3, or E3, and n equals to 2, or E2. But also, there's other wavelengths of light that can be emitted for this atom. So one other way is we can have the n equals to 2 down to the n equals to 1. In this case, it goes from 1.5 to 0. Well, that difference is 1.5 EV. So again, we can do 1240 divided by 1.5 EV, And we can see that this difference here is actually equal to 896 nanometers. So in other words, that's in the infrared. That's beyond the visible spectrum. So I'm sorry, I said 896, 827. You're probably looking at me like, what is he talking about? Okay, 827 nanometers. If you went from n equals to 2 to n equals to 1. But also, you could go from n equals to 3 down to n equals to 1, in which case that's 4 down to 0. So again, we can use this equation here and say 1240 divided by 4, and that's 310 nanometers. So in other words, going from this top down to the bottom state here, I can say that this arrow is going to be 310 nanometers difference of energy. So that's kind of interesting. So now you're getting an idea that the smaller the difference is between the states, well, the longer the wavelength is. Okay, very good. So hopefully that made sense. And again, just to remind you, this is a good formula to have tucked into your notes and will be applicable for our final exam as well. I will ask you a few different questions where I'll give you the wavelength in nanometers, and I'll ask you what the energy is in EV, and I'll also ask you for some sense making around some of those things as well. We'll also look at differences in energy levels, and those differences in energy levels then will be related to a wavelength. So those are the different wavelengths of light that can be emitted, and those wavelengths will appear in the system's emission spectrum. So in other words, the spectrum, if we were to have some kind of meter that could measure all the different light, well, we would see a peak and another peak and another peak. Maybe they would have different intensities, but we'd see one at 310 nanometers. We'd see another one at 496 nanometers, and we'd see another one at 826 nanometers. We'd see these little peaks that correspond to the emissions of the different differences in energy level for these atoms. Okay, so atoms have these discrete energy levels, and so this is another aspect of the quantum. So we looked at quantum in the sense that light has this particle nature, or this discretized particle nature, but also atoms, because of their wave-like nature, have these interferences, and that creates these discrete energy levels. So this quantized energy level is another aspect of quantum physics. And so you can see that there's these different allowed energy levels, but one interesting thing is that the electron is not allowed to go to an energy level in between, which is really weird, actually, if you think about it. That's like saying I can walk at 2 miles an hour, and I can run at 5 miles an hour, but it'd be like saying, well, you can't go a speed that's somewhere between 2 and 5 miles an hour. Wouldn't you think that would be strange if you couldn't go every speed in between? That's how strange this is. So here's the pictorial system that shows you that if you wanted to make a transition from n equals to 1 to n equals to 3, you'd have to go between 10 eV up to 90 eV. In other words, a difference of 80 eV. And of course, we could again convert that into a wavelength. In other words, 1240 divided by 80, that's 15.5 nanometers. So that's extreme ultraviolet, right? So we're talking about extreme ultraviolet in these cases here. And so conservation of energy then requires that when an electron changes its energy level, then the photon is either created or it's absorbed with exactly that amount of energy. Okay. So we did this question here. We looked at the different wavelengths that can be emitted for this atom. Now let's go on and look at another aspect of the wave-like nature of particles. So here's a strange thing. Heisenberg's uncertainty principle says that you can't know exactly where an object is and how fast it's moving at the same time. You can't do both. This might sound like a really strange thing to do, but people have that it's not possible. But it turns out people have tried to measure this and tried to measure it, and as far as we know, this is the real deal. So here's a little comic here that says, website wants to know your location. Do you want to allow or deny it? I'm sure all of you have seen this kind of thing on your phone. You might say, okay, I allow it. And then the person looks at their phone again and it says, now the website wants to know your momentum. And they say, haha, nice try, right? Because they know Heisenberg's uncertainty principle. This is a nerd comic called XKCD. And so this idea here was created by Werner Heisenberg, who was a German physicist, I guess back in the 1901. Yeah, okay. And he was very active in the 30s, 1920s, 1930s, and so on. And basically came up with this idea that the uncertainty in momentum multiplied by the uncertainty in position, that's this q here, is on the order of Planck's constant. That's really weird. So that's saying that if you knew your position really, 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 really well, let's say that this delta q is on the order of 10 to the minus 34, right? You know, Planck's constant is 10 to the minus 34-ish. Then your delta p would be really large to make this be equal. So that's something strange and interesting. So the uncertainty principle then basically says that your delta x times delta p has to be at least h, and then there's this prefactor over 4 pi. There's also an uncertainty principle that involves energy and time, and we might also talk about that as well. So will the uncertainty principle help the Giants pitcher Madison Bumgarner with his pitching? So let's make an example. If we had a 150 gram baseball, that's where I got that 150 grams from earlier, is because I was thinking about that problem. Thrown at let's say 93 miles an hour. That's a pretty fast pitch. So that's 42 meters per second, but plus or minus 1 meters per second. Okay, so the uncertainty in the position is now calculated. So we should try to figure out how to get the uncertainty then in the position and see if that maybe helps him with this pitching situation. Okay, so I'm going to write down the equation here that delta x times delta p has got to be greater than or equal to h over 4 pi. Okay? So my delta v is going to be equal to 1 meters per second. And my delta v is 1 meters per second. So that means that my delta p is equal to m times delta v. Let's say that we don't have any uncertainty in our mass, just to keep things simple. So the mass is 0.15 kilos times 1 meters per second. So math is pretty easy here up to this point. That's 0.15. And of course the units for momentum is a little bit weird, kilograms, meters per second. But now this allows us to plug in this value up here for our delta p. So our delta x then has got to be greater than h over 4 pi times delta p. So let's give it a try and see what we get. So if we have h, which is our 6.626 times 10 to the minus 34, divided by 4 pi times delta p, which is 0.15. Well, this value here is 3.5 times 10 to the minus 34 meters. So that means that here's our person pitching the baseball. There's baseball cap. Oh, you can't see what I'm writing. It's beautiful artwork. They throw the ball, right? And here's the batter. They're trying to swing the bat. That's a baseball bat. I know it's not the most gifted artwork, but and maybe they use 2 hands. It's probably best to use 2 hands when you're trying to play baseball. And this ball here, according to quantum mechanics, it's saying that this ball could be shifted up or shifted down by 10 to the minus 34 meters. That's not very much compared with the size of the ball, right? So the size of the ball is something like 5 centimeters. And so fractionally, you could say that you know, if we were to blow up this whole picture here like that it could be a little bit lower, right? Or a little bit higher, or a little bit to one side, right? Or a little bit to the other side by a extremely small fraction. But it kind of gives you an idea of like how then this quantum stuff relates to the real world. And also, the other thing that I want to bring up is that this is the reason why we've never really experienced this kind of stuff, and it never really came up in discussions about how physics works, right? It was a fairly recent thing. This is the last 100 years that people actually started thinking about this, you know? We've been thinking about science for a long time now, thousands of years, but it's only been the last 100 years that we actually even thought about this kind of thing. And this is why, is because the effect would be so, so tiny, 10 to the minus 34, that we would never actually witness this kind of thing. Okay, so here's an interesting thing, is that it is something that we can actually make use of. And one of those things is called an electron microscope. And I won't get into all the details right now. Your book actually has some nice explanation of electron microscope. I'll just point you out to which page it is here. This is on page 1007. And we're actually able to use the wave-like nature of electrons to image things that would normally be too small for a normal microscope. So when we are trying to do a normal microscope, we usually have some light beam that comes into a lens, and then it focuses it down to a very small place. And the smaller that you can focus this down to, this is our converging lens. So maybe this reminds you of some things that we've seen before, converging lens. The smaller that you can get with this thing here is related to it's basically related to the wavelength. I'll say that the smallest that you can focus this thing is about the wavelength. Okay, it depends on how you define things, and it could actually be wavelength divided by 2. But for our discussions, you can this is good enough that the smaller you can focus something is basically limited by the wavelength. So, for example, if I tried to use 500 nanometer light, then the smallest feature that I can see, right, is going to be 500 nanometers, okay? So here's something a little bit kind of strange or interesting. Let's look up something. We're going to look up the coronavirus. And I'm going to look it up as an image. And actually, I want to look it up as size. I'm sure everybody looks up the coronavirus. So let's look up coronavirus size. And we're faced with these images of the virus and what it actually looks like, right? So it's this kind of ball, basically, with these spikes here. I won't get into all the biology of things, right, and how it reproduces and how it propagates and so on. But if you wanted to see this thing, I was hoping that it would give a diameter. Let's see here. It's usually on the order of about 200 nanometers. Let's see. So I'm looking up a scanning electron microscope of a virus. This is one, but without the scale, so it doesn't show us how big it is. That one's too small for us to see. Bear with me here. Well, I guess what I'm trying to say is, let's just imagine for a moment that the size of this virus is actually 100 nanometers across. That's usually about the right size. I'm sorry that I can't come up with it right on the spot for the size of the virus. But let's say that you wanted to do some science because you really wanted to learn about how this virus works and how it propagates, what it looks like, and what the different features are. You know, so being able to label these different proteins, being able to get a better grip on how does this thing actually work. If you wanted to do that, one thing that you could do is to try to take an image of it. But unfortunately, if you're using 500 nanometer light, in other words, visible light, you're not going to be able to see the virus. It's going to look like a big blur. So you could say, well, okay, I know what I'm going to do. I'm going to go down to 100 nanometer light. That's going to be ultraviolet light. Well, it's kind of difficult to make ultraviolet light, and it's difficult to detect it, and it's difficult to have optics that work with it. And if you wanted to go even shorter, now we'd be talking about X-rays. But there's another way that we can do things here, and that is to create electrons that have a wavelength that's very, very short. And so, in other words, remember the de Broglie wavelength, which is h divided by p. If we wanted to have a wavelength, let's just say that we wanted to have a wavelength that was 1 nanometer in size, then mv is equal to h over lambda. In other words, we can, if we wanted to accelerate electrons, we can say it's h over lambda times m. And so if we wanted, we can say 6.626, that's our de Broglie. The wavelength that we wanted, let's say, is 1.0 nanometers. And the mass of an electron is 9.11 times 10 to the minus 31 kilograms. So let's put these numbers all together and see, well, what kind of speeds would we actually need to accelerate an electron if we wanted to make use of the wave-like nature of an electron. So if we divide this by 1 nanometer, that's 10 to the minus 9, times 9.11 times 10 to the minus 31. Well, this number looks big, but 700,000, right? 730 kilometers per second is not an unreasonable speed, actually. That number, for example, let's say if we wanted to say half mv squared as the kinetic energy, if we wanted to send it through a voltage, right, we can figure out, well, what kind of voltage will we need to send this electron through if we wanted to accelerate it up to these speeds. Let's do this. Delta V, then, the voltage, is going to be equal to a half mv squared divided by q. So this is, we're trying to just figure out, well, what kind of voltage will we need to actually accelerate electrons to 730 kilometers per second or 730,000 kilometers per second. Well, if I did 0.5 times the mass of the electron times this v squared, so I'm just going to copy this number here because that's the number that we got, that number squared, and then divided by the mass of an electron, well, that's not very much. That's just 1.5 volts. So in other words, if we just accelerate the electron through 1.5 volts, we'll get these enormous speeds. And if we get enormous speeds, then we get a short de Broglie wavelength, right? That's on the order of, well, I'll say dB for de Broglie wavelength, is 1 nanometer. So you only need to accelerate an electron through 1.5 volts in order to get it to go quickly enough. And so, you know, there's some details here. How do you actually make use of it? How do you actually, how do you actually accomplish these things in practice? And basically what you have is there's like a filament that creates a bunch of electrons, and then you send it through kind of a screen, and then you basically have a plate on the other side, and there is usually some positive and negative terminals, and so then the electrons are accelerated, very similar to that photoelectric experiment that we saw in the last lecture. And they're accelerated, but then before they become accelerated, then there's actually some focusing mechanisms where you put some charges here on either side and then focus them down into a very small spot. And so that spot then, the size of that spot, can be on the order of the wavelength, which is what we were finding earlier. So then instead of having a beam of light, we can have a beam of a beam of electrons. And instead of an actual lens, we'll have some charged areas here, which will actually force the electrons to focus down to a small size, and now they can be on the order of 1 nanometer. And so in other words, we can actually then focus those electrons to a very, very small size, an electron beam, and this is called an electron microscope. So that is an interesting thing, and you can get these beautiful images where you really, really get a lot of detail. Okay? So electron microscopes make use of the de Broglie wavelength of an electron. There's also something called a scanning tunneling microscope that has a little tip and brings the tip near the surface of a material that also makes use of this wave-like nature of electrons. And this is a really cool image because this is actually data from placing single atoms around in a corral, and you can actually see the waves of putting two atoms inside. They create these matter waves which cause interferences. So that's just a little taste of the de Broglie wavelength of matter. In other words, that matter has wave-like properties, and it can be useful for something like a scanning electron microscope. Okay, so next time we'll be taking a look at atoms and molecules. Specifically, we'll be looking at spectroscopy, and we'll look at a simple model for the hydrogen atom, which then extrapolates out to different kinds of atoms. And we'll also review some of the consequences of quantum mechanics and how it's used to describe atoms, such as the Pauli exclusion principle. So we're going to be continuing on with this idea that differences in energy levels, like we saw here, lead to either the absorption or the emission of photons. And one of the things that we'll be curious about is that can we make a model for an actual atom, like for maybe a hydrogen atom or some other kind of atom, and can we use that to then describe what kind of physics is really happening inside? So yeah, so that's kind of where we're heading, and that's what we're doing for next time. As we do move into chapter 29, I just would like to maybe refresh your memory and also point you in the right direction that at the appendix of your book, then there's a periodic table of the elements. And so if you do have a copy of your book with you, this is a great resource here. I suppose that maybe the lighting is good enough that you can get all the information that you need just from taking a screenshot of this if you needed to, if for some reason you don't have the textbook with you or handy. This is a good thing to have. We will be talking about the different atoms and this notation. One of the things that I'll just kind of bring to your attention is that these numbers up here, the 1, 2, 3, and 4, these are going to be the number of protons that are in an atom. And turns out that for a neutral atom, then there's going to have to be the same number of electrons as there are protons, because the protons have just the opposite charge as an electron, which is that 1.6 times 10 to the minus 19 coulombs. And so if we have a balanced, in other words, just as many electrons as neutrons, just as many electrons as protons, then we'll have an uncharged atom. Now, it's not always the case that there has to be the same number of protons as neutrons, and you can see here, for example, that carbon has a mass of 12, which means that there's 6 protons, which means that the other 6 that make up the mass of this thing, right? So this is basically saying it has 6 equivalent kind of proton or neutron masses. The mass of a proton, mass of the neutron are about the same as each other. And actually, I've been putting together a study guide for you all for the final exam, and that I've put on there some useful numbers. And so one of these numbers here shows you that the mass of the proton and the mass of the neutron are basically about the same. Mass of the electron is about 2,000 times less compared with the mass of the proton or the neutron. So for carbon, you can see that there's 6 protons, and if the atomic mass is 12, that means that there's also 6 neutrons. Same thing for nitrogen, same thing for oxygen. It's like, okay, if there's 8 protons, then that must mean that there's also 8 neutrons. But if you look at fluorine here, well, that one is 19 but 9. So if 9 of them are protons, that means that the other 10 that makes up 19 total, the other 10 are going to need to be neutrons. So there's 10 neutrons in this case, but only 9 protons. So I just wanted to help you to start to get you familiar with the elements through the periodic table. We'll talk some more about how they work, how to read the periodic table, how to read the different the notation, and we'll look at the orbital levels and all that kind of cool stuff, and I'll show you some simulations. But I just wanted to at least get you familiar with how this works. That's right at the end of your text. It's the so-called A3, or this is like Appendix B, I guess, is what it is. So just look in the appendix of your book and you'll find this periodic table. This will be useful as you're going through the reading through the chapter for chapter 29. Okay, we will see you next time and hope you have a good day.